All right. So is it true that the product of the derivative is equal to the derivative of the product? Let's think about what that statement is really asking. Is it true that the product of the derivative would be equal to the derivative of the product? The answer in this case needs some verification. To 2x squared plus 3, its derivative is 4x, right? We know that now. 2 times 2 is 4. Take 1 away, it's x. Derivative of 3 is 0. G of x is equal to 4x minus 1. And its derivative would be 4. Because derivative of 4x is 4. Derivative of 1 is 0. So what we want to do then is answer the question at hand, which is the derivative of two things multiplied together the same as the derivative of their derivatives multiplied together? So let's talk about it. What would be f times g? Go ahead and multiply and FOIL out f of x times g of x. So I want you to multiply and FOIL out f of x times g of x. Because that is the old way, right? The old way says you would have to multiply the two functions together, get them to a single polynomial. So we get 8x cubed plus 12x minus 2x squared minus 3. So the function f times g would be equal to that. The derivative of that then would be equal to 24x squared plus 12 minus 4x, and then a 0. So f of x times g of x, its derivative would be equal to the derivative of its polynomial, which is 24x squared plus 12 minus 4x. If I did it the opposing way, and I took the derivatives of f and g, f prime of x times g prime of x would give me 4x times 4, which is 16x. Is the derivative of the two functions multiplied together's derivative the same as the derivative of the derivatives multiplied together? Are these two the same? No, they're not even close to each other, right? So which one's the correct derivative of the two functions multiplied together? A or B? How many of you think A is the correct derivative? How many of you think B is the correct derivative? How many of you didn't vote at all? What? Okay. Yes. Let's reason through why one makes more sense than the other. When we took derivatives of linear functions, what type of derivative did we get back? Constant. If you took the derivative of a cubic, what type of function did you get back? Quadratic. So if f is a quadratic and g is linear, you multiply them together to get a cubic. So the derivative of a cubic should be a their derivatives are linear and constant to give you a linear. Does a linear function meet that qualifications of being a quadratic? No. So the correct answer was A. You have to multiply together two functions before you can find their derivatives. So you can't find like the derivative of f and the derivative of g and magically multiply the derivatives together and hope it's the same thing. That leads us to the product rule. The product rule says, that if the derivative of a product is the first function multiplied by the derivative of the second, then we have the following equation. You will hear me say the product rule all the time. It's the first times derivative of the second plus the second times derivative of the first. When I talk about first and second, I am talking about the functions f and g. F is the first function we're multiplying. G is the second function we're multiplying. So the derivative of the functions is the first times derivative of the second plus the second times derivative of the first. So it's first times derivative of the second plus second times derivative of the first. Always and forever. So let's apply the power rule. We will call x squared plus 1 the first, or f of x. X cubed plus 3 is the second, or like the g of x. So the derivative dy dx is equal to the first. So we simply rewrite x squared plus 1 times the derivative of the second. So the derivative of x cubed is 3x squared. Derivative of 3 is 0. Plus the second times derivative of the first. So derivative of x squared is 2x. Derivative of 1 is 0. So you have first times derivative of the second plus second times derivative of the first. Now we have to clean this up algebraically. So we get 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x. Combining like terms, I get 5x to the fourth plus 3x squared plus 6x. If I did not know the product rule, how else could I have found the derivative of this problem? Yes. Exactly. So if you forgot the product rule, which hopefully you don't, you could have done this by taking y and foiling those two binomials together. So x squared times x cubed gave you x to the fifth plus x cubed plus 3x squared plus 3. And then found the derivative of that. So derivative of x to the fifth is 5x to the fourth. Derivative of x cubed is 3x squared. And derivative of 3x squared is 6x. So what you should notice is that I get the exact same answer for both. In all fairness, I'm not sure not foiling this type of problem at the beginning and then taking the derivative isn't easier than the product rule. Now that won't be true for all derivatives with product rules, but this is a case where if you forgot the product rule, you could FOIL and then derive. Yes?
Did the product rule work for second and third derivatives?
Explain what you're asking.
Like, if you need to take the third derivative of that of the same y equals x plus 1,
So you mean like back here, instead of FOIling this out, you want to take the derivative of these terms like this?
But if it was like, if you're taking the f triple prime.
Yeah, like that would be right now. So, yeah, like I could do d2y dx squared. And then again, I could leave these unmultiplied together, and you could do the first times derivative of the second plus the second times derivative of the first plus the first times derivative of the second plus the second. Running out of board. Times derivative of the first. If you didn't FOIL them together, correct? But like here, if I had multiplied them together and got the answer that was in my yellow box, like I could just say the derivative of this is 20x cubed plus 6x plus 6. And believe it or not, if you would multiply all of this out, that's what you would get. Yeah. So that's why when you were asking that, I was like, sure. But like I guess I didn't understand like the logic behind it, because in this case, you would want to get rid of the product rule because you are now creating like it multiplies down. Yep. Now my screen's all wonky. Okay, so example number 2 is a case where like foiling it doesn't help you as much because now you got square roots and squares and linears and non-linears all sort of mixed together. So using the product rule here kind of helps eliminate those messier problems. Anytime we have a square root, we want to change it to a radical, or from a radical to a 1/2 power. So I'm going to think of the square root of x really like x to the 1/2. So that when I multiply this through, I'm using x to the 1/2. So dy dx is the first times derivative of the second plus the second times derivative of the first and then you have to distribute and combine like terms. So 4x times x to the 1/2 is like adding 1 to 1/2. So you get 4x to the 3/2, which is the same as 4 square roots of x cubed. Four times 2 is 8x squared. And then over here, you have to actually FOIL because you have two binomials. So 1/2 times 2 is 1. X squared minus 1/2 gives x to the 3/2. 2 times 2 is 4x squared. And 1/2 times 5 is 5/2. Since that was x to the negative 1/2, it would drop to the denominator as a positive. And 2 times 5, which is 10. So here, when you're simplifying or getting down to your final answers, and I'm just erasing that for purpose of space, we have x to the 3/2, which is a like term with 4x to the 3/2. You have 8x squared, which is a like term to 4x squared. So 4 plus 1 is 5x to the 3/2. 8 plus 4 is 12x squared. And then plus 5/2 square roots of x plus 10. You can, as a square root. You could write it as 5x to the square root of x even. Any and all of those are fine. The biggie is making sure this is in your denominator. They will not accept negative exponents. All exponents must be positive. Yes. Well, they said that Delta Math wasn't accepting it, but when I looked, I think it was just more that their timing wasn't accepting it. Okay, example 3. You got 1 over x plus x squared. We need to rewrite fractions as negative exponents, or you need to FOIL to start. So again, there are 2 ways you could go about doing this problem. You could say y equals x to the negative 1 plus x squared times x to the negative 1 plus x cubed, and use the product rule for that. So that you add the first times derivative of the second. So the power rule says exponent down in front. Take 1 away. Plus the second times derivative of the first. And then you have to FOIL twice. So is this the logical method for this problem? Is the product rule the logical method based on what's happening right now? No. Guys, the product rule is not always the smarter choice. That's what I keep trying to reiterate. The product rule is a great alternative, and it will come in handy many, many, many times. In this case, the product rule requires me to FOIL twice with lots of negative coefficients and constants. We're going to finish it out, and then we're going to compare to if I had FOILed at the beginning. Negative 1 plus negative 2 is negative 3. So that's first, outer, inner. X squared times x to the negative 2 gives you x to the 0. What do we know about x to the 0? It's like a 1. So that's really like a negative 1. X to the negative 1, x to the negative 2. Give x to the negative 3. X to the negative 1 times x is x to the 0 again, which is 2. Minus 3x, because 3 minus 2 is 1. Plus 2x to the 4th. Combining like terms, negative 1x cubed and negative 1x to the negative 3 give negative 2 over x cubed. Positive 3x and negative 3x cancel. Negative 1 and positive 2 give a plus 1. 3x to the 4th and 2x to the 4th give 5x to the 4th. Let's do it again. But let's do it now. by foiling at the beginning. So off to the side or somewhere on your paper, let's do it again, but foiling from the beginning. So now y equals first. So 1 over x times 1 over x would give 1 over x squared. X cubed divided by x gives x squared. X squared divided by x gives x. And x cubed and x squared gets x to the 5th. This is kind of like the same as x to the negative 2. So there's my negative 2, x to the negative 3, 2x, that 1, and 5x to the 4th. Drop your negative exponent down. And way less foiling. So again, there are instances where it is way more helpful to foil at the beginning. Yes, because I think I missed, like my 2x was over here and I just never wrote it down at the final. Let me go back. I can undo all this. No, it's okay. I just have to, like, click a bajillion times. We're gonna let it think for a minute. And it's not like before where I could just go back to a slide. Clear. So there are a variety of ways to represent derivatives. In physics, you actually don't use notation so much, you use words. So we talked about that in physics. You use velocity, acceleration. In mathematics, we tend to use function notation. So we have our f and our f prime and our f double prime. God bless you. So in calculus, the same holds true. The most common, if you start with a y, your first derivative is y prime. The second is y double prime, y triple prime, and then you have y to the 4th, and any value after that uses Roman numerals. We like to talk about it in terms of function notation. The most common form is Leibniz, which is we're taking the derivative of y with respect to x. So if you're taking the derivative of y with respect to x, then this becomes dy dx. The second derivative is d2y for the derivative twice with respect to variable x twice. So you get x squared. Then you have d cubed y, dx cubed, and so on and so forth. function notation, like f of x, is just like the y's. So it goes to Roman numerals afterwards. So it's like f prime x, etc. We also can see a capital letter D for derivative. The capital letter was like what's on your higher order when you start to take derivatives way up there. It's a capital letter D, and then the number for the derivative you're taking. So in this case, it would be D1, D2, D3, D4. And then let's do the physics relationship. So the original function is position. The derivative of position is velocity. The derivative of velocity, or the second derivative, is acceleration. The derivative of acceleration is the jerk. So if you think about something accelerating and then you kind of changing that acceleration, the object would jerk, or like getting hit by another car. You get your whiplash. That's sort of that third derivative equation. And then the derivative of a jerk is a snap. So you could think of the jerk and snap from the movie. Oh my gosh, can't think of it with Reese Witherspoon. Legally Blonde. Yeah, see? Now you know what comes after acceleration is the jerk and snap. So the connection to all of it, we have first and second derivatives, and we can take higher order derivatives using power and product rules. So we can make that connection between them. So this is kind of like a position function. You have t cubed minus 6t squared plus 9t. The first derivative would be f prime t. So 3t squared minus 12t plus 9. The second derivative, 6t minus 12. And the third derivative is 6. In section 4, we talk about particles of motion. So we're going to do a lot more with this type of example. They talk about changing directions, extrema, and so forth. Okay, so your homework is that next page in the packet. You are looking at the product rule.